So the upcoming assignments that are due coming this Wednesday, February 24th, discussion 3A. I see a few people have already done parts of the discussion, but remember there are 2 threads this week and they are due Wednesday. The due date I couldn't change, go in and manually change, so they might be marked as late, but I won't dock any points. So just get them in by Wednesday at midnight. So you have 2 parts, 2 threads. One of them is where you are picking 2 elements and doing the electronegativity calculation that was shown earlier in this video, where you use the electronegativity table, you subtract the electronegativities of the 2 elements that you chose, and then see what area it falls in. Is it nonpolar? Is it polar? Is it ionic? Okay. The other discussion thread wants you to give an example of a chemical formula. So we looked at several chemical formulas, both covalent formulas and ionic. So you would give a formula and then tell me whether it's covalent or an ionic compound, and then give the name of it. So that's the other discussion. Also, questions 3A for the McGraw-Hill Connect questions, those 15 questions that are assigned that were originally due this last Sunday. The deadline's been extended to Wednesday, February 24th. This coming Sunday, on the 28th, we have discussion 3B, which also has 2 threads and videos, and then the 3B questions. So, so far, we're going to stick with this schedule, having those 2 items due on Sunday. If that changes, I will let you know by Thursday at the latest. Otherwise, we'll plan on getting those in by Sunday. So if you have any questions, don't hesitate to email, reach out, and we'll get it all figured out. Okay, so kind of going to do a slideshow. I might need to jump in or out of the slideshow, but it's just a review of the Chapter 3A material. And then the discussion as well as the Chapter 3A questions have both been, due dates have been extended to Wednesday. So if you haven't done those yet, you can still do those. I haven't changed any other due dates, but that doesn't mean that I won't. I just want to see how things go once we get back in the classroom, and then we'll extend test dates or whatever we need to once we see what's what, kind of when we all get back together. So trying to, from current slide, there we go. All right, so I can kind of skip that. So last time we actually saw each other in person, I briefly mentioned what valence electrons were. It was after we got done talking about electron configurations, I believe. So valence electrons are the electrons involved in bonding. So the reason I'm bringing this up now is because we're going to be talking about actual bonds. And when we talk about bonds, whether we're talking about covalently bonded compounds or ionically bonded compounds, the valence electrons is what's involved in those bonds. Okay, so that's the key that I wanted to kind of bring away from this slide, is those valence electrons that I briefly touched upon. Those are the electrons, the outer shell electrons, that are going to be involved in bonding. So we're going to look at the types of bonding there are, look at how to name different compounds given their chemical formulas, and things like that. But before we do that, let's look at the types more specifically. So we have ionic bonding, which is going to be a transfer of electrons. So that means the metal is going to give away electrons, and the non-metal portion is going to accept electrons. So since one is donating and one is receiving, we're going to see ions. We're going to see charges, plus signs, minus signs, all that. For covalent bonds, this is where they're sharing. So nobody's giving anything up, nobody's taking anything from anyone else. They're sharing the electrons together. So there's no charges involved because nobody lost anything, nobody gained anything. They're sharing the electrons. Now with covalent, this can be separated into 2 types. And this is where one of the discussion section comes from. And the 2 types of covalent bonds are nonpolar covalent and polar covalent. So nonpolar is when they share equally. So what that means is when we look at their electronegativities, and electronegativity is when It's the atom's affinity for electrons. So it's how much they want the electrons. Okay, that's what electronegativity is. So the more that atom wants the electrons, the more electronegative it is. Okay, so we're going to use electronegativity to figure out if it's a nonpolar bond or a polar covalent bond. So nonpolar is where they share equally. So this would be where their electronegativities are very similar because both atoms involved want the electrons the same amount. For polar covalent, this is where the two atoms involved, their electronegativities are very different. And since they're different, that means one's more electronegative, meaning one wants the electrons more than the other atom. And if it wants the electrons more, it's going to it's not going to share them equally. It's going to take a little bit more of that negative charge to its side. And I know that can be kind of confusing. So the next slide is trying to show a picture of that occurring. So we have all three types here of, let me move this up to the top. I don't know if you're going to be able to see this. We have all three types of bonds here. So the first one in blue is a covalent. And then we have the polar covalent in the middle, and then a full ionic bond with a separation, complete separation of charge for ionic. So this blue kind of egg-shaped circle, I guess you would call it, oval, this is showing the electron cloud. So these two X's, these are representing the atoms. Okay, so this is atom A and atom B. Okay. Now the two dots in the center, that's an electron pair. So those are actually representing two electrons. So that blue electron cloud around it, since it is completely egg-shaped, completely oval-shaped, that's showing that those electrons are being shared equally because it's symmetrical. Okay, so a nonpolar covalent bond, you would see a symmetrical electron cloud shape because both of the atoms involved are sharing those electrons equally. They have a similar electronegativity. Now with polar, so in the middle here in the green, you'll notice it's not symmetrical anymore. Over here by the Y atom, the electron cloud's a little bit bigger. And that's because atom Y is more electronegative than atom X in this case. And since it's more electronegative, it means it wants those electrons more. So it's not going to share them equally anymore. What it's doing is it's taking more of the electrons than X has. So Y wants the electrons more, so it's taking more of that electron cloud. So that's why we have this delta negative sign above the Y, because that's saying that Y is partially negative. It's not an ion, because there's no complete separation of charge. It's just partially negative because Y wants those electrons more than X does.
And instead of an oval, it's more of an elongate shape, like
yeah, it's more of an egg shape than the other one. So I was saying egg shape for the covalent bond, and that was a mistake because the covalent bond, the non-polar covalent bond, I should be more specific, is symmetrical, whereas the polar is more of an egg shape.
Gotcha.
So you can also see too, but over by X, there's a partial positive sign. That's just saying it doesn't have as much of the electrons as Y does, so it's partially positive. But okay. For ionic compounds, what happens is you don't have this partial anymore. Notice there's even a break between the two. They're not even touching. The electron clouds aren't even touching. And that's because with ionic, there's a transfer. So X literally gave electrons away to Y. So they're not sharing anything. One gave electrons to the other. So you'll see a complete separation of charge for ionic. So we can actually use.
So there are two different.
Go ahead. Yeah, two different atoms.
So they're two different, like they're two different. Okay. That's what I was making sure I was looking at that picture right.
Yep. So we can use numbers, the electronegativity values, to figure out what type of bond it is by doing a subtraction. And that's what we're going to look at next, is that subtraction. And so this next slide here, this is what you're going to be using for the discussion. This is what's going to help you do the discussion. So one of the discussion questions, I believe I wrote it down here. Yeah, at the very bottom here. where you pick any two elements, and we're going to use the electronegativity calculation that we're about to talk about to figure out if a bond between those two elements is polar, nonpolar, or if it's ionic. So we just looked at diagrams of what that looks like. So a nonpolar covalent bond would be a symmetrical electron cloud where the electrons are shared equally. A polar covalent bond would be that egg-shaped where one of the atoms involved wants the electrons more. And then we have ionic bond where it's a completely two different atoms, electrons have been transferred. So we can figure that out, what type it is, using this electronegativity table. So this has all the atoms on it, like a regular periodic table. The difference is we have these numbers below each element, and those numbers, that's their electronegativity value. So there are no units on electronegativity value. We're just using it as a source to figure out the type of bond. So looking at the calculation, so I have under number 2 here, it says delta En. That delta En just means change in electronegativity. So whenever you have a change in anything, you're subtracting. You're taking the final minus the initial. And in this case, we're going to take the electronegativity of one atom and subtract it from the electronegativity of another atom. Now, notice there's also bars around it. Those bars are absolute value bars, just like when we do percent error calculations. So all that means is we're always going to get positive. Okay, so if you happen to get a negative, just change that sign to a positive. Once you have the value, so once we do this subtraction, that's what this last portion is for. So this is a chart telling you, okay, where does your value fall in? What range does your value fall into? Does it fall into the nonpolar, which would be anywhere between 0 and 0.5? Does it fall into the polar covalent bond area, 0.5 and 1.9? Or if it's higher than 1.9, meaning its electronegativity difference is huge, then it's going to be an ionic bond. Because if the electronegativity difference is very large, what's going to happen is they're not going to share the electrons at all. Instead, one of them is just going to give the electrons to the other one. All right, so what you would do in the discussion and how we're going to use this is you would just give me any two elements on the periodic table. Okay, so the example I have here is I chose boron and hydrogen. I put a dash between them because that's just how we represent a bond. A dash, a line is a single bond. So if I choose boron and hydrogen, then I simply find them on this electronegativity periodic table and I subtract their values. So let me change color here, it might be easier. Boron, I'm going to circle in this orange color. So notice its electronegativity value was 2.04. So I wrote that down first. And it doesn't matter which one you write first because it's absolute value, right? It's going to be a positive number no matter what. So boron was 2.04 and then hydrogen up here is 2.20. And I forgot the 0. That's my fault. Let me add it here. So 2.20, just so our sig figs are correct, because we want to go out 2 decimal places. Okay, so when I subtract those, I'm going to get a negative 0.16, but because of the absolute value signs, I just change it to a positive. And then I use this number and I see what range does it fall in. So it is 0.16, and that's less than 0.15. That means it falls into this category, the non-polar covalent bond. So if I had a bond between boron and hydrogen, I would classify it based off of my calculation as a non-polar covalent bond. So in the discussion, you would do the exact same thing. Pick any two elements, and it can even be a transition element. Doesn't have to be a main group. Pick any two elements, subtract them, and then tell me what range they fall in. Are they nonpolar, are they polar, or are they ionic? Does that make sense?
Yes, ma'am.
Okay. So next we'll look at the bonds themselves. So we talked a little bit about Using electronegativity values, how to tell if it's polar covalent, non-polar covalent, or ionic. Now what we're going to look at is naming compounds. So when we're naming covalent compounds, it does not matter if it's a polar covalent or if it's non-polar. That doesn't matter, we're going to name them the same. Okay, so you don't have to do any calculations to figure out how to name a covalent compound. So how do you know if it's a covalent compound? Well, if you have a nonmetal with a nonmetal, so I have this color-coded periodic table up here, all the nonmetals are in yellow. So if the two elements involved are in the yellow shaded regions, then it's a covalent compound. Also, semimetals with nonmetals are often covalent compounds as well. So like we saw in the previous slide, and I can even go back to it, I believe. Here we go. Between boron and hydrogen, well, boron's a semimetal, right? It's along that zigzag line. But when boron was with hydrogen, we said that through the calculation, it was a nonpolar covalent bond. So semimetals and nonmetals can also be covalent bonds. So nonmetal with a nonmetal or a semimetal with a nonmetal. All right, so how do we name them? Well, we're going to name them using prefixes. So the next slide's all about naming them. And this is kind of a review. So I haven't, if you want to see more detailed step-by-step, go ahead and watch those PowerPoints I posted. But what I'm going to do here is just show you the key elements of naming a covalent compound. So what I have shown here is I have 3 chemical formulas listed. All of these are representing covalent compounds. And to prove that, you can look at the periodic table and see, for instance, phosphorus and oxygen, they're both nonmetals. The next example has hydrogen and sulfur, also both nonmetals. The last example has boron, which is a semimetal, and then hydrogen, which is a nonmetal. So just based off where those elements on the periodic table are, I know that those are all covalent compounds. So that's the first step when you're naming any type of chemical formula that you're given. The first step before you name it is, what is it? Is it covalent or is it ionic? Because there's different rules depending on the type of compound. So in this case, since we're looking at covalent, we're going to use prefixes. So I have prefix written up here for both the first element present and a prefix for the second element present. Now the first element, after we write the prefix, we're going to write the element name just how it's written on the periodic table. The second element present is going to change a little bit. So instead of writing just the element name, we're going to add an IDE ending on the end of it. And what I have off to the right are how all the elements change with the IDE endings. And then I also have the prefixes that we're going to use. So naming the first one. The number after the P is a 2. So what that tells me is there are 2 atoms of phosphorus. So I'm going to find the prefix for 2. What is that? Di. So it's going to be di. And then phosphorus is just going to remain phosphorus. We are not going to add any endings to it since it is the first element present. And I'm writing with a mouse right now, so that is why my writing is sloppier than usual. So diphosphorus will be the first name, the first word to name it. Then we have to look at oxygen. Now oxygen, since it's covalent compound, we want to use a prefix. So we look at the subscript after oxygen to figure out what that prefix should be. And it's a 5. And 5 tells me penta. But I don't want to write pentaoxygen because since oxygen is the second element present in that chemical formula, I want to make sure I'm writing the IDE version of it. So oxygen, when I go over to the IDE endings, we see it changes into oxide. Not oxygenide, but oxide. So it'll be pentaoxide. Try typing this instead. All right. You want to try the next one? Or do you want me to do it?
I think I I think what, like, the way you're explaining is making perfect sense.
Okay.
So it would be, so we have, it's hydrogen, but I look at the number after it, so it's dihydrogen.
Yep.
And since sulfur is part of the IDE stem, it would be dihydrogen sulfide.
Almost. Sulfide, yes, but you need a prefix. What's the prefix? How many?
Monosulfide.
Monosulfide, yes. So
It's
since
just one.
there is no number after it, it's just one, exactly. So when you don't see a number, you just assume it's a 1. So since there's 1, we're going to write monosulfide. And this last example is kind of tricky because it's an exception to the rule. But for this last one, BH, go ahead.
Would it just be boron?
Just boron. Do you remember why?
And then boron, well, isn't it because mono only applies when it's the second one?
Yes.
Like, that's what I thought.
So boron, not monoboron, because there's only one, and you can only write mono if it's the second element present, and then hydrogen becomes
Trihydride.
Trihydride. There's 3 of them, so tri and then hydride. Good. So I like the covalent compounds. To me, they're a little bit easier to name. Just because they're, and when you look at the periodic table, you can see that too. Like the covalent compounds, the nonmetals are this tiny little section. So I think that aids in the fact that they're easier, but all right. So we need to be able to, given the chemical formula, write the names, but we also need to be able to go reverse. Meaning if I give a name, you need to be able to come up with the chemical formula. And that's what this slide is all about. It's showing a name at the bottom here in the example. So dinitrogen tetroxide. So the fact that this name has prefixes in it tells me it's a covalent compound because we only use prefixes for covalent compounds. So you won't see di, tri, tetra, any of that when it's ionic. So those prefixes tell us how many of each element. So for dinitrogen, we'd have to look up nitrogen on the periodic table. We would write its symbol, which is just an N. And then the di part tells us how many. So di means 2, so we'd write N2. So that's the first part of our chemical formula. The second portion, tetraoxide, well, oxide, that's just the IDE form of oxygen. So the chemical symbol for oxygen is just an O. And then we use the prefix to tell us how many, what the number is going to be. So tetra is 4 when we look at our prefix table. So N2O4 would be the chemical formula for that one. So those ones are nice just because they tell you how many of each by using a prefix. So let's get into the hard ones.
Right.
Ionic compounds is the hard ones because as you can see, ionic is a metal with a nonmetal, and our metals make up most of the periodic table. It's all those ones in that pinky fuchsia color. So with ionic compounds, remember this is where we're transferring electrons. So we're going to see plus signs, we're going to see minus signs. You won't see the plus and minus signs in the formula. So notice here I have CaCl2. So that's just the chemical formula. And the formula itself is always going to be neutral because the charge on calcium and the charges on the chlorines are canceling each other out. So the compound's neutral, but the parts that make up the compound are charged. So calcium has a charge, chlorine has a charge, but together those charges cancel out. So let's look at how to name these. Before I go about naming them, this is something that was covered in chapter 2, but we kind of missed Friday of chapter 2, not last Friday, but the Friday before. So I wanted to do a quick review of valence electrons and ions in general, since we're going to be using them to help us name ionic compounds. So what I have here is the periodic table shown. We have the main group elements in red and the transition elements in yellow. And I have these numbers across the top. So these numbers across the top, these are representing the number of valence electrons of the main group elements. So this was one of the discussion questions you had to do, not this, like a week ago, over a week ago.
The one that was due before the snow.
Yes, thank you. The one that was due before the snow. And it's where you had to pick a main group element and then just tell me how many valence electrons it has. Because if you're looking at a main group element, you just look at what group it's in and that will tell you. So it just goes in order 1 through 8. Now we use the valence electrons and we apply the octet rule to figure out what the charges of the main group elements are going to be. So that sounds confusing, but the goal of all the main group elements is to have 8 electrons. That's what they want in their outer shell. Everybody wants 8 valence electrons. Now the noble gases already have them. So notice this last group we called the noble gases. They have an 8 above them. That's because they already have 8 valence electrons, with the exception of helium. He only has 2. But that's why the noble gases are inert. That's why they're not reactive. It's because they have a full octet. They have 8 electrons in their outer shell. They're happy, they're stable. Everybody else, though, doesn't, right? The halogens have 7. The alkali metals have just 1 valence electron way over here. Alkaline earth just have 2. So the goal is for all of those other elements, they want to get 8. Some of them are going to lose electrons to get 8 valence in their outer shell. Some are going to gain to get 8 in their outer shell. So for instance, I like to use the halogens as a good example because the halogens are this group here right next to the noble gases. And they have 7 valence electrons in their outer shell. So we just said everybody wants 8. So if the halogens have 7 and they want to get 8, the easiest way to get 8 is just to gain 1 more. Okay, so if they gain 1 more electron, they'll have 8, they'll be happy. But when they gain 1 electron, they're now going to be charged. So we can use this to figure out what exactly the charge should be. Okay, well, if you gain 1 negative charge, you will become negatively charged because that's what electrons are. It's a negative charged particle. So using that knowledge of valence electrons, we can figure out what the charges of each group should be. Okay, so we just looked at the halogens, which is this group right here. And we said they had 7 valence electrons. Well, notice on this slide, it's showing what their most probable ion is, what their charge is. Well, halogens usually form a -1. They will always form a -1 in this class. And that's because they have 7 valence electrons. And when they gain 1 more to get their full octet, they have a -1 charge. The group right next to it with oxygen, sulfur, and selenium, they have a -2 charge, and that's because they are 2 away from being a noble gas. Nitrogen, phosphorus, arsenic, they form a -3 charge, and that's because they are, if you count it, 1, 2, 3 away from being a noble gas. Okay, so all the nonmetals gain electrons, become negatively charged to get their full octet. The metals, so if we look over here at the alkali metals in group 1, notice they have a +1 charge. Well, that's because the alkali metals have 1 valence electron. And in order to get a full octet, they can do 2 things. They can either gain 7 more or lose 1. And it's much easier for them to lose that 1 valence electron than it would be for them to gain 7. Okay, so if they lose just that 1, they are losing a negative charge, thus becoming positively charged. Okay, so basically all the main group elements are going through the path of least resistance to get a full octet. The metals lose electrons, the nonmetals will gain electrons to get there. And using this chart here, you can predict what their charge will always be for the main group. We can't do that for transition, but we can do it for the main group elements. So we're going to take this knowledge these probable ions that they form into naming. We're going to need this when we name compounds, as well as when we come up with the compound's chemical formula if we're given the name. All right. So I'm going to kind of open.
Can you go back to the octet rule definition real quick?
Absolutely.
Thank you.
Yep. So since ionic compounds are encompassing the entire periodic table, there's a lot more variations. So we're going to start with the ones that are easier to name that involve these main group elements, the ones in red. And then we'll look at polyatomics.
I got it.
Transition elements. So there's a lot of different areas, but we'll start small and work our way up. So that's what I have down here, the 3 different types of ionic compounds that we're going to name. So we're going to start with the standard ones, the main group ones. Then we'll look at the polyatomic table. And then last but not least, we'll bring in those transition metals. But like I said, we want to start small. So right now we're going to look at main group only. So with the main group elements, we have the metals, which are the alkali and alkaline earth metals, bonding with a nonmetal. That's the definition of an ionic compound, is a metal with a nonmetal. All right, so when we name them, first and foremost, no prefixes. It's ionic now, so we're not looking at prefixes at all. No mono, di, tri, any of that. That's only for covalent. So to name these, they're actually a little bit easier to name than covalent because you don't need the prefixes. So you'll notice in the chemical formula, so for this first one, we have Na2O. So the metal portion always comes first. Because Na is sodium, it's an alkali metal in the first group. So the metal portion always comes first in the chemical formula. Then the non-metal portion comes second. Now I still have, what are these called, suffixes? Subscripts, there we go. We still have subscripts like before, but we're not using the subscripts to name it. So even though I have 2 sodiums, I'm not going to use that number 2 to name it at all. So I'm not going to say disodium, for example. Instead, Na, I just said was sodium, so I'm going to name that part first, and I'm going to name it straight off the periodic table, no alternate endings, no prefixes involved. So just sodium. Now for the nonmetal portion, or the second element present, we aren't going to use prefixes, but we are still using that IDE ending. So oxygen still becomes oxide. All right, here's another one, MgCl2. So it is an ionic compound because magnesium's a metal, it's an alkaline earth metal. Chlorine's a nonmetal, it's one of those halogens. So to name it, magnesium, no prefixes, no alternate endings, and then chlorine becomes?
Chloride.
Chloride, exactly. And there's 2 chlorines, but that doesn't matter for ionic. We're not going to write dichloride, we're just going to write chloride. Let me put up the other one while I'm trying to write this. Chloride. Okay, last one example I have is KBr. So K, the metal portion, potassium, and then Br is bromine, another halogen. It's a nonmetal. So to name that one, same exact steps. The first element, potassium, just write out potassium, no alternate endings, no prefixes. And then bromine becomes?
Bromide.
Bromide. All right, so those are the easier version of the ionic ones, or when we just have main group. All right, let's look at doing the reverse now. So what I have here is the name of an ionic compound. How do I know it's ionic? I can find those elements on the periodic table. Calcium, Number 20 here, notice it's a metal. And then hydride is just the IDE version of hydrogen. And even though hydrogen's over here, remember hydrogen is a nonmetal. It belongs, as you can see in this picture, it's right next to helium over here because it's a nonmetal just like helium is. So we have a metal with a nonmetal, that tells me it's ionic. How do I write the chemical formula? Whenever you're writing a chemical formula for ionic, you need to start by writing the chemical symbol of both elements involved and the charges. And we can use where they are on the periodic table to figure out the charge. So calcium is Ca. What should calcium's charge be?
+2.
+2. It's in group 2, so it loses 2 electrons to form a +2 cation. Okay, and then hydrogen is just an H. Now notice hydrogen, according to this periodic table, it can be a +1 or it can be a -1. Now in this case, I know it's a -1 only because I can't have 2 positive ions making a bond. That will never happen because remember, opposites attract. So I'm going to need a positive atom with a negative atom. That's the only way they're going to be attracted to each other. So that's how I know in this case, this hydrogen is a -1. I just want to, is there any questions on that? No, it's kind of a hard.
No, that's making sense right now.
Okay. So now I have calcium with a 2+, hydrogen with a -1. All right, well, as we said earlier, with an ionic compound, when we're looking at the chemical formula, the compound itself is neutral. It's the parts that have charges. So our goal now is to make this compound neutral. We need the positives and the negatives to cancel each other out. Right now, if I had 1 calcium and 1 hydrogen, are those charges canceling?
No.
No, I have a +2 and a -1. So that's not going to cancel. I'm going to have too many pluses. So what I need to do is add another hydrogen atom because that hydrogen atoms have a -1 charge. So now if I have 2 hydrogen atoms, that means my total negative side will be -2, right? A -1 plus a -1 equals -2. Now on the cation side, the positive side, I have just 1 calcium atom, and that calcium atom is worth +2. So I have a +2 on the cation side, a -2 on the anion side, and when I add those together, they cancel each other out, equaling 0. Agreed?
Agreed.
So that tells me I need 1 calcium, so my formula will be Ca1, and I don't have to write the 1 because it's just assumed. And then hydrogen, I'm going to have 2 of them. That's what we decided. We needed 2 of these atoms to cancel out that positive charge. So I'm going to write H sub 2. So CaH2 is the correct chemical formula for calcium hydride. So that's what you're going to have to do every time you're trying to write a chemical formula of an ionic compound. You have to write the elements with their charges and then figure out what the formula is by making that compound neutral. All right, stop me if you have any questions.
I'm good right now.
Okay. So, and we'll look at some examples, but more examples of that, but I want to cover the other areas first so that we can bring it all together. So we're going to look at polyatomic ions next. So polyatomic ions is this list or this table that I have listed here. So there's also a copy of this table in the week 5 folder, I believe, because we're looking at week 5 material. So you can print that off or just have it available whenever you're doing homework assignments or the exam. So these are not all the polyatomic ions that exist. These are just the most common ones that you'll see in this course. So what polyatomic ions are is 2 or more elements that are covalently bound, meaning that they're sharing electrons, but they have an overall charge. So you'll notice all of these ions listed have either a minus or a plus. So they are indeed ions. They have negative charges and positive charges. So since they have negative charges or positive charges, we can use them in ionic compounds. They can be part of an ionic compound. We only have one cation that we'll see in this course, and by cation, I mean a positively charged ion, and that's ammonium. So I want to point this out because for the most part, there's negatives. What that means is, for the most part, we're going to see polyatomic ions as the second portion of a chemical formula, because it's always cation first and then anion. So these are going to be present in chemical formulas. So what we're going to look at next is, how do you know if a polyatomic is present? Because that's kind of the tricky part, is trying to figure out how you know. So to figure out how we know, we're going to use some examples. So the first example that I have, the first chemical formula shown, is Li3PO4. Okay, so how do I know there's a polyatomic in here? Well, if you ever have more than 2 elements present and one's a metal, there's going to be a polyatomic somewhere in there. Okay, so in this case, I have Li, which is lithium, I have P, which is phosphorus, and O, which is oxygen. So that means I have 3 elements present. So if I have 3 elements present, that tells me something in there is a polyatomic. Okay, so that's when you go to your polyatomic table and try to figure out which portion of that formula is the polyatomic and which portion is the cation. So in this case, PO4, this whole section here, is the polyatomic. And most of the time, it's the second portion of the formula that's the polyatomic. And that's the case here as well, right? PO4 is the second part, so that's the polyatomic. So how do you name these? Just like before. We take the cation or the metal portion, we name that first, straight off the periodic table, no prefixes. Okay, so Li3 is just lithium. Doesn't matter that there's 3 of them. We're not using that 3 in the naming at all. So we have lithium for the first part. Now for the PO4, we just identified that as a polyatomic. So you would go over to your polyatomic table, you would find PO4, and then write its corresponding name. So in this case, PO4 is phosphate. So we just write lithium phosphate is the name of that guy. Oops. The next example, we have parentheses. So that's another hint that there's a polyatomic involved. If there's 3 or more elements, or if there's parentheses involved at all. You will only see parentheses in this course if there's a polyatomic. Notice I say in this course, there's always exceptions to everything. But all right, so we have Ba, which is barium, and then the portion that's in the parentheses, that's the polyatomic. Okay, so we're going to name it the same way. We start with the metal. In this case, Ba is barium. For the second portion, NO3, we look up NO3 on the polyatomic table and write the corresponding name. Where is NO3? There it is. NO3 in this case, lost my mouse, is nitrate. So barium nitrate would be the correct name. All right. I also want to point out with endings. So notice all of the endings that we see are either ATE or ITE. So we have a few ITEs as well. There's only, I think there's only 1 or 2 IDEs. Yeah. So, and we're going to look at the opposite of this as well. But the reason I'm pointing out the endings is because if you see, given a name, an ATE or an ITE, that tells you it's a polyatomic. Because the only time that you'll see IDE is if it's a main group element or if it's cyanide or hydroxide. Those are the only two IDE polyatomics, are cyanide and hydroxide. Any other time you see IDE, it's a nonmetal from the periodic table. All right, let's name this last guy here. So this last guy, notice I have parentheses, so I know a polyatomic's involved. So NH4 is in parentheses, so that's the polyatomic portion, at least one of them. NH4 is ammonium. I'm spelling it wrong, but I'm also using a mouse, so it's going to look horrible either way. All right, so I have ammonium. Now the second part, CO3, well, there's two elements present there. So I can't write carbonide, trioxide, like there's no way to name that using our conventional methods because there's two elements present. So if there's two elements present, that tells me that's another polyatomic. So I would find CO3 on my polyatomic table, which is getting kind of messy since I'm using all these words here. And it is carbonate. So it would be ammonium carbonate would be the name for that guy. ATE. Oops. There we go. Saved me a lot longer to write these with mouse than I anticipated. Questions on polyatomics so far?
Not right now. That table is helping.
That table helps. Okay, good.
Yeah.
So what these are, this is a hodgepodge of everything we've seen so far. So some of them have polyatomics in them, some of them do not. Okay. The reason I wanted to show this is because you're not going to be told, hey, this is an ionic compound with a polyatomic in it. You're going to have to figure that out using just the name itself. Okay, so in the first name, we have potassium chloride. So if we wanted to write the chemical formula for that, we would get out our periodic table and figure out what the symbols were and their charges. So potassium is K. It's an alkali metal, so it has a +1 charge. Now the second portion, chloride, since it has an IDE ending, that tells me that it's an element from the periodic table, not a polyatomic. So chloride is just the IDE version of chlorine. Looking at the charges, it's a halogen, so it's going to have a -1 charge. So what should my chemical formula look like? Well, my goal here is to make sure their charges cancel. And look, they already do. I have a +1 and a -1, right? So that means I just need one of each. So the chemical formula would just be KCl. The next one, strontium bromide. So strontium is an alkaline earth metal with the symbol Sr. It's in group 2. So it has a +2 charge. And then bromide, once again, we're seeing that IDE ending. So that means it's most likely an element from the periodic table. So bromide is just the IDE version of bromine. So Br is the symbol, -1 charge because it's a halogen. All halogens like to form a -1. Now in this case, the charges aren't canceling each other out. So we need to have more bromines. So another way of doing this is called the crisscross method. I show it in the PowerPoints, but I didn't talk about it today. And what that is where you take the value of the charge and make it a subscript. So this 2 would be a subscript on bromine, and the 1 would be a subscript on strontium. So what that means is I need 1 strontium and 2 bromines. So Sr1 and then 2 bromines, so Br2. So that would be the correct chemical formula. Red's kind of a bad color to use. All right, Potassium nitride's next. So we already looked at potassium. It's K with a +1. Now I have IDE ending again. So that means that nitride is an element from the periodic table. And more specifically, it's actually nitrogen. And nitrogen has a -3 charge. That's its most probable ion, is -3. Because it has 5 valence electrons and it wants to gain 3 to become noble gas configuration. So doing the crisscross method, oops, we need 1 nitrogen and 3 potassiums. So it would be K3N. Horrible writing. So all the ones we've looked at so far have IDE endings, which tells us that they're elements from the periodic table. But the next example, notice now we have ATE. So since it's an ATE ending, that tells me it's not an element from the periodic table, it's a polyatomic. So I would need to look up nitrate on the polyatomic table, write its chemical formula and its charge. So I'm going to start with magnesium. Magnesium is an alkaline earth metal. It has a +2 charge because it's in group 2. But the nitrate part, that's the part I get from the polyatomic table. So I might be able to skip back. Oh, it's not going to let me skip back. Sorry. I guess I could just skip to this one. So I have NO3 with a -1. That's what nitrate is. So that's why the charges are written on there for you, because you're going to need to use the charges to figure out chemical formulas. So for this one, I need to take the 2 that's on magnesium, and that's going to be a subscript on the NO3. It's telling me I need 2 NO3 ions for every 1 magnesium ion. So when I write this, I just said I needed 1 magnesium ion, so it's going to be Mg with a 1. And then NO3, I needed 2 of those. So if I need 2 NO3s, I need to make sure when I'm using polyatomics, if there's more than one of them, I have to put parentheses around the entire polyatomic. So NO3, I put parentheses around that entire thing, and then I put the 2 on the outside of the parentheses. Because otherwise, if I don't put the parentheses there, it's going to look like I need 32 oxygens. And I don't want 32 oxygens, I want 2 NO3s. The last example, aluminum sulfate, is the same thing. We see the ATE ending, and that's what leads us to finding this SO4. ATE tells me it's a polyatomic. I look at my polyatomic table, I find sulfate, and I see that it's SO4 with a -2. So to do this one, I'm going to need 2 aluminums. That's what this charge up here tells me. This 2 is going to become the subscript on aluminum. So I need 2 aluminums. And then since there's a +3 charge on aluminum, that means I need 3 SO4s. So I'm going to put parentheses around SO4. And then I'm going to put that 3 on the outside. Is there questions on this?
The table's really helping.
Okay. And it does just take some practice too. And this is, yeah, longer than I expected. So what I'll probably do, I'm going to most likely have to change some dates for the exam, because on Wednesday, I'm going to cover the transition metals since we're running out of time. And the transition metals are just involving this whole center section here. So with the transition metals, we don't know the charges. So that's where they get tricky, because the transition can have multiple charges. So we're going to have to use what the transition metal is attached to figure out its charge. So we'll look at transition metals, how to figure out the charge for transition metals, and then how to name transition metals on Wednesday. And that should only take the first 10 or 15 minutes of class. And then if there's no questions at that point, I'll move on to chapter 3B material, where I'll look at Lewis structures and things. But this assignment is due on Wednesday at midnight. So if you haven't done it yet, look at it, bring any questions that you have on Wednesday so that you can get that submitted by midnight on Wednesday.